Okay, we're looking at a friction problem here. We have a 30 kilogram box on a flat floor. We're given that the coefficient of kinetic friction between the floor and the box is 0.35, and we want to know how hard you have to push to move the box across the floor at constant speed. So if we look at the system schema, we have the person, the box, and the earth/floor. I'm going to put those two together. So the person's definitely pushing the box, right, with this normal force, maybe call it NP. The earth is pulling on the box with the weight of the box, and the floor is also doing another, having another interaction with the box. That's going to be kinetic friction, and we now know that the expression for that is mu sub k times the normal force between the surfaces. That normal force, that would is the one we want is the normal force between the floor and the box, which we haven't put in yet actually. So there we go. So there's actually three interactions between the box and the earth: the weight, the normal force, and the friction force. The person has some other interactions here, but we really only care about the box, so we've gotten all those, so we'll stop there. For our free body diagram, we have the normal force from the floor up, the weight down. This is for the box. The person is pushing forward with that normal force of person, and friction is resisting that. We're going to label that mu sub k times n, and the n that we want is the normal force between the floor and the box, because it's the normal force between the two surfaces that's important for the friction. So that's this interface here, not this one. Not normal person, but normal floor. Why are they all balanced? Because the velocity is constant. It doesn't matter what constant velocity we have, as long as the velocity is constant. This is what the force diagram will look like. I'll make right and up positive. I'll write my F-net equations now. In the x dimension, I have NP in the positive direction, minus mu sub k times NF. That's the negative direction. And because the forces are balanced, this equals 0. In the y dimension, I have the floor pushing up, the mg down. I called up positive. So that also equals 0 because those forces are balanced. So at this point, you can plug in some numbers if you want to. The normal force of the person, that's what we're looking for. The coefficient of kinetic friction is 0.35 times the normal of the floor. We don't know what that is yet, but we can get it from over here. So the normal of the floor minus the 30 kilogram mass times 10 newtons per kilogram equals 0. So the normal of the floor exerted by the floor is 300 newtons. We can put that back in over here. Move that over. 0.35 times 300 newtons, which will be 105 newtons. So that's how hard you need to push this box across the floor at constant speed. If this kinetic friction coefficient is bigger, then you'll have to push harder. So if the surfaces are stickier, you'll have to push harder, which makes sense. And if the normal force is bigger, you'll have to push harder as well. So easiest way to do that is to make it a bigger box, a heavier box. All right, there it is.